Having a look at question 6, we'll see this is a projectiles question, but this question involves vectors. Vectors are kind of optional. They're meant to be a tool that helps you work. So if you're unhappy using vectors, you could do this question without using vectors and just do it using standard projectiles instead. But this is meant to make things easier, so we're going to persevere with vectors. So we get told it gets hit with velocity this, so we've got a horizontal and vertical component, and these are going to end up being, in terms of alpha, the velocity, so the angle of elevation that it's hit with. This is a point of 0.9 meters above the ground, and we get some information here that after 3 seconds it strikes the ground a horizontal distance of this away from our start point. So we're going to use particle motion and just gravity to model this. So we're going to use vectors. So we're going to put in the start of our journey, we're going to put in 3 seconds for this journey, because we get told that it strikes the ground 3 seconds and it travels this horizontal distance. So for our distance, we're going to put this in as 57.6 I, because we've travelled a horizontal distance of 57.6, and we've travelled down 0.9 meters, so we're going to put this as minus 0.9 j. This bit's actually really important because these things aren't at the same height. If we just put in that, we'll actually find a point over here. We need to put in this extra downwards from the start, going downwards 0.9 meters. Our initial speed is pi plus qj. I'm going to use capital P's and capital Q's because I struggle to make them not look like 9s, so we're going to go with that. Our final velocity is not involved in this question. Our acceleration is minus 9.8 j. The j just means it goes downwards and there's no acceleration in any other direction other than vertically. So you'll notice that s and u and v and a are all vectors. All we need to do now is put this into a Suvat equation. We're going to use, because v isn't involved in the question, we're going to use s equals ut plus a half at squared. So putting this in, we get 57.6 I minus 0.9 j equals this, so 3 pi plus 3 qj, 3 times u, plus a half, minus 9.8 9.8 j, and we're going to multiply this by t squared, which is a 9. So let's tidy all of this up. We have 57.6 I minus 0.9 j equals 3 pi plus 3 qj. I'm going to multiply all these things together, so I get a half 0.5 times minus 9.8 times 9, which gives me this number here, which is probably better put as a decimal, which is minus 44.1 j. So we've got this equation here, which just governs our journey for the first 3 seconds. We're asked to work out some values. We're asked to work out the value of p and the value of q. We can use our either projectile motion equations to arrive here, or we can use this to find our value of I and our value of j. So if we look at this, we'll notice that there's an I equation, I, just 2 i's, and there's a j equation here. So using the i's only, we get 57.6 equals 3p. There's some i's, all these other ones are j's. Because horizontal and vertical are at right angles to each other, we can treat them separately. So we get p equals, we're going to do our 57.6 divide 3, which gives us an answer of 19.2 ms to the minus 1. So there's p. For the j ones, we get minus 0.9 equals 3q minus 44.1. So we're going to add this over, so we're going to get 44.1 minus 0.9, and then we're going to divide this by 3, and we arrive at q equals 44.1 minus 0.9 all over 3, which equals 14.4. If we go back to the question, we'll notice that this was a show that for q. So if you just jump straight from here to q equals 14.4, you are not going to get full marks. We need to show where q has come from, because it says show that, we need to show every possible step. So we used vectors here to do both the projectile motion equations at the same time. You can do this without vectors, you can do it as two separate equations if you want, but vectors can be quite a useful tool for modelling projectiles. The next part of this is to find the initial speed of the ball. So we should be able to pick out that its initial velocity is pi, so 19.2 I, plus qj, 14.4 j. So the speed is just going to be the size of velocity. It's the modulus of velocity, which is the square root of 19.2 squared plus 14.4 squared. So I'm going to take my answer from before. So 14.4 squared plus 19.6 squared, and then we're going to square root answer, which is going to leave us with 24.3211. So v is 24 s to the minus 1. So here is our speed. We could actually label this speed rather than velocity. So we get that. For the part D, we're asked to find the exact value of tan alpha. So if we draw ourselves a little rectangle, so this is for part D. If we draw ourselves a little rectangle, we know that this is going 19.2 along and 14.4 up. So we can find this angle with tan alpha is 14.4 over 19.2. So if I do 14.4 divide 19.2 on a calculator, I get 3/4. We could do tan minus 1 to find this angle, but we're asked in the question to find the exact value of tan alpha, so we're not going to go any further, and it was only 1 mark. For the last part of this, we were asked to find the time for which the cricket ball is at least 4 meters above the ground. So if we go back to the picture, I can draw on a line here at about 4. So we'll notice that there are going to be 2 times where this crosses. So we're going to form a quadratic, we're going to get our 2 equations out of here. We've got choices here. We could use just standard suvat, or we could use vectors. Because we're just interested in vertical motion, I'm going to take out the vectors part, but if you want to use vectors, you're welcome to use vectors. It doesn't say anywhere in here that we have to use vectors, so it's entirely up to us. So we're going to write out a suvat for vertical. So our suvat, S-U-V-A-T, we've got our 0.9 here, our path here, and we want to know a distance of 4 meters. So the distance we want to move is up 3.1 meters. So plus 3.1. I'm going to count upwards and this way to be positive. So we need to go up 3.1 meters because we're already at a height of 0.9 and we want time to start from this bit here. We only want to go up 3.1. So our initial speed in the vertical plane is q, which is 14.4. Our final speed isn't involved in this question at all. Our a is minus 9.8, and we're going to call our value here t. So we're going to use s equals ut plus a half a t squared. Filling in our information, we get 3.1 equals 14.4 t minus a half, sorry, plus a half minus 9.8 t squared. I'm going to take everything over to this side, so I'm going to get 4.9 from half of that t squared. I'm going to get rid of the minus by taking it over here, minus 14.4t plus 3.1 equals 0. This looks like the kind of quadratic our calculator should be doing for us, so I'm going to use the quadratic equation solver on my calculator to get this. It's a polynomial of degree 2. Polynomial just means multiple powers, and it's degree 2, so it's quadratic. So I put in 4.9 equals minus 14.4 equals 3.1 equals, press equals again, I get t equals 2.7049 and t equals, press it again, 0.33 no, 8, sorry, 23389. So here are two times. So this one here is going to be the first one, this one is going to be the second one. To find the the time in the air, we're just going to subtract these things. 2.7049 take away 0.23389 gives us this number here, which is t equals 2.47101, or t equals 2.47 seconds. Maximum, very maximum of 3 significant figures. You can do it as 2 or you can do it as 3.